This is the Mid-Atlantic Senior Physicist Group monthly talk by Nat Gopalswamy. I guess I got that close enough.
Yeah.
And usually we introduce ourselves. We have two guests here. I don't know if they want to introduce themselves, but my name is Don Novotny, and I'm the chairman of the group. So, Paul, you want to introduce yourself?
Yeah, I'm Paul Rodriguez, retired from Naval Research Laboratory.
Oh, yeah, I forgot to say that I'm retired from NIST. Okay, Howard?
Hi, I'm Howard Gordon. Everybody calls me Flash, and I'm retired from NSA, National Security Agency.
Okay, Jerry?
I'm Jerry Stenbakken, retired from National Institute of Standards and Technology as well.
Okay, Adnan, do you want to introduce yourself?
Sure. My name is Nat Gopalswamy. I work at Goddard Space Flight Center in the Heliophysics Division, Solar Physics Laboratory 671.
Okay, Zachary?
Sure. Good morning. I'm Zachary Harvey. I work at Lawrence Berkeley National Lab. I just saw this seminar and it caught my eye. It's pertinent to a job that I may be beginning soon, and I just thought I'd listen in.
Okay, well, welcome aboard.
Thanks.
Okay, David?
Maybe as a practicing
Okay. Well, I guess that goes through, I don't know, Med-Eden. Ali, you want to introduce yourself?
I think he would probably be only able to do it through the chat since he wasn't able to unmute himself.
Right.
Well, okay. Okay, we'll go ahead. Paul, you want to introduce the speaker?
Okay, this is Nat Gopalswamy. And should I read the brief bio first or the abstract?
Read the bio.
I'm sorry, I didn't hear that.
Read the bio.
Okay. Nat Gopalswamy is an astrophysicist at NASA's Goddard Space Flight Center, Solar Physics Laboratory, Heliophysics Science Division. His research is in the area of solar and solar terrestrial physics, including coronal mass ejections, solar flares, solar energetic particles, solar radio bursts, interplanetary shocks, and space weather. He is also involved in coronagraphy and radio astronomy. He is a co-investigator of the Solar Terrestrial Relations Observatory, whose acronym is STEREO, and the principal investigator of the balloon-borne investigation of temperature and speed of electrons in the corona, also referred to by the acronym BITSI. He directs the Coordinated Data Analysis Workshop, or CDAW, a data center that provides data on solar eruptions since 1996. He has authored or co-authored more than 475 scientific articles and has edited 9 books. His publications have received more than 23,000 citations, yielding a Hirsch index of 81. He is the executive director of the International Space Weather Initiative, past president of the Scientific Committee on Solar Terrestrial Physics, or SCOTEP, and the vice chair of COSPAR's panel on space weather. He has received numerous awards, including the 2013 NASA Leadership Medal 2017 John C. Lindsay Memorial Award for Space Science, and the Astronomical Geophysical Union Space Physics and Aeronomy Richard Carrington Award in 2019. He was conferred with a doctor honoris causa by the Bulgarian Academy of Sciences in 2019. He is a fellow of the American Geophysical Union and the International Science Council. He received his PhD in physics from the Indian Institute of Science in 1982 and received postdoctoral training in radio astronomy at the University of Maryland in College Park in 1985. The abstract of his talk, or the title of his talk, is Coronal Mass Ejections and Solar Gamma Ray Emission. So I'll read you his abstract. Sustained gamma ray emission from the sun is characterized by a time-extended emission well beyond the impulsive phase of solar flares. These gamma rays are also referred to by the initial SGRE, which stands for sustained gamma ray emission. So SGRE was first identified by Forrest in 1985 using data from the Solar Maximum Emissions Gamma Ray Spectrometer. Only a handful of SGRE events were known over the next 30 years until the advent of the Fermi satellite's Large Area Telescope, or LAT. Fermi LAT has detected more than 36 of these events, which help us obtain their statistical properties and their association with solar eruptive events. These events help us understand the origin of the greater than 300 MeV protons that interact with the solar chromosphere, produce neutral pions, which then decay into the observed gamma rays. SGRE events are associated with solar flares of X-ray class M and X, large solar energetic particle, or SEP events, interplanetary type 2 radio bursts, and superfast, greater than 2,000 kilometers per second, coronal mass ejections. And coronal mass ejections are referred to as CMEs. All these eruptive phenomena are related to one another. Energetic CMEs drive shocks that accelerate protons observed as SEPs and electrons resulting in type 2 radio bursts. Particles are also accelerated in the flare reconnection region, which is a spatially compact region on the surface of the sun. The flare particles are responsible for various impulsive phase emissions, including gamma rays, which have properties different from those of the SGREs. Some authors attribute even SGREs to flare accelerated protons trapped in flare loops, although their close connection to SEPs, type 2 bursts, and CMEs point to an extended source, namely the shock driven by the CMEs. In this talk, Nat will review the properties of SGRE events and the associated phenomena, and the current understanding of this elusive energetic phenomena. So Nat, the floor is yours. You can continue as you begin.
Thank you very much, Paul. That was an extended introduction, and the reading the abstract is very useful. So I'm sure people are familiar with this terminology. So let me proceed with my talk. Let me share my screen again. All right, can you see my screen?
Yeah.
All right.
Yes,
so
we
let me-
can.
Okay. All right, thank you very much for this opportunity to speak to you about coronal mass ejections and solar gamma ray emission. And the main contributor to this presentation is data from the Fermi satellite, which has got this instrument called the Large Area Telescope. And I will be presenting data from this mission. And also coronal mass ejections from two missions. One is the SOHO mission, the Solar and Heliospheric Observatory, which has got a chronograph that observes CMEs, and also stereo mission that has chronographs observing CMEs as well. And I will also be using solar.
I believe we just lost a link due to a battery problem.
Let's see. Let's see. Well, his name is here.
You may have to reconnect or something to a power source.
Yeah, you may have to sign in again.
Says it's no video. Nat, can you hear us?
Yeah, I saw a brief flash of a battery saying there was a battery problem, low battery.
Got to find the charging unit.
He's back. Yeah.
I'm back. I'm sorry. I don't know. I was kicked out for some reason. I couldn't figure out why.
Okay, sorry about that, but it seems like that was beyond our control.
Okay, no
Yeah.
problem. So let me go back. Okay, can you see my screen again?
Yes, we can see it.
Okay, all right. So coronal mass ejections. And I just mentioned that we observe mass CMEs from a chronograph on board the SOHO mission. And you see a movie, which is a series of images taken by SOHO. And this is over a period of, the whole day on 2012, May 17.
You're not sharing your screen right now.
Oh, okay, let me do it again.
Mm.
So.
There we go.
Got it?
Yeah.
Okay, sorry about that. Okay, so what you're seeing is a movie taken by the chronographs on board the SOHO mission. And what the movie is basically a series of images taken every 10 minutes or so, and then put together in the form of a movie. So what you're seeing is basically a mass ejection coming from the sun. And then you see all this flickering like a snowstorm, right? This flickering is nothing but energetic particles accelerated by the big CME. And those particles come and hit the detector, which observes the CME. So essentially, before the CME goes into the interplanetary medium, the particles, they are very fast. So they arrive at the SOHO detector and they produce this noise in the CCD. So basically the flickerings are energetic particles, or the effect of energetic particles on the detector. So this, so you see two, maybe more than one mass ejection here, the big one, and then you have smaller ones going up here, slow one, and then there's a diffuse one going to the left. So that this tells you that only some CMEs accelerate particles, and that property that makes the CMEs accelerate particles is basically their speed. The speed, if it exceeds the local characteristic speed, which is the magnetosonic speed, then they drive a fast mode MHD shock. And this shock picks up particles from the corona and interplanetary medium, accelerates them, and spits back into space. The particles can go up, and if they come to Earth, we can detect them as energetic particle event, or SEP, solar energetic particle event. And so this is one of the important aspect of the topic today, that the energetic particles. Now, the CME speeds can range from less than 100 kilometers per second to more than 4,000 kilometers per second. And obviously, you can tell that the ones at the higher end of speed are the ones going to accelerate particles, because they are very energetic, drive shocks, and the shocks accelerate particles. The average mass of CMEs is like about 1 billion ton, 10 to the 15 grams. And the higher ones are the more energetic ones will have up to 100 billion tons, 10 to the 17 grams.
Wow.
The kinetic energy of these mass ejections, you can just see from the mass and the speed. The average is about 10 to the 30 ergs, or 10 to the 23 joules. And the higher, the more energetic ones can have energy up to 10 to the power of 33 ergs, which is 10 to the 26 joules. So they are very energetic ones. And in fact, the most energetic phenomenon in the heliosphere. So if you plot the plot a histogram of speeds, you can see that the average is only 400 kilometers per second. But the ones we are interested in are in the tail, more than 1,000 kilometers per second, and they are the energetic ones which accelerate particles. And the middle panel shows the width of the CMEs, which is basically in the sky plane, you have an average angular width. That is, the average width is about 40 degrees. But the real big one can have up to 3 times as wide as this average value. And then lastly, I show CME acceleration. What is shown here is the acceleration in the interplanetary medium, which is generally negative. That means the CMEs are slowing down already. But the initial acceleration, because CMEs starts from 0 speed to attain a big speed and then start decelerating. So the peak speed can be much higher, and also the acceleration, initial acceleration, is always positive, of course, and that can be up to 10 kilometers per second, kilometer per second square. Okay, so they're very, very fast accelerating ones. And they also vary with solar cycle. What you see is up and down is basically CME rate is very high during solar maximum phase, and up to about 1/2 to 1 during the minimum phase. Minimum phase, of course, had no sunspots, but even then CMEs come from the sun, because CMEs originate from non-sunspot magnetic regions also on the sun.
So, Nat, question, the acceleration that's caused by what, electrostatic or electric?
It's Lorentz
repulsion.
force. Lorentz force.
I'm sorry, say that again, please.
Lorentz force. Basically, you have B cross B, J cross B. So the magnetic field and current interaction.
Okay.
And you can also see the plot. The red one is the CME rate. And then in the background is the sunspot number, which is an index of solar activity. And you can clearly see that during maximum phase, you have more CMEs, and minimum phase, you have very few CMEs. So this tells that it's closely related to sunspots. But as I mentioned, there is another component which is not related to sunspots, but they are from other magnetic regions on the sun. Sometimes magnetic regions on the sun may not have sunspots. Some people call them spotless regions. But the bottom line is you need to have a closed magnetic field on the sun, like a sunspot region. And the CMEs originate when there is some kind of non-potential configuration of the magnetic field, which means they possess free energy. That free energy is released by a mechanism known as magnetic reconnection. And that's how the CMEs are ejected. And when the CMEs are ejected, you have what is known as solar flares formed on the sun. So solar flares are basically structures that are stationary, stuck on the sun. Simultaneously, you have a magnetic structure ejected from the sun. That is the CME. When the CME arrives at Earth, we can pass through it, spacecraft pass through it, and they can measure the magnetic field, the density, speed, and all those things. And we find that the magnetic structure of a CME is a flux rope. It's like a helical structure. It has an axis, and then the field lines wind around that axis. And this flux rope is formed due to the reconnection process I mentioned. So CMEs are associated with a number of other solar phenomena. One is, of course, solar flare, I already mentioned. And the solar flares are kind of a collateral phenomenon taking place when the CME starts. And then CMEs are associated with shocks if they are fast enough, if they are super magnetosonic. And these shocks accelerate particles. Of course, those SEP events, or solar energetic particle events, are also associated with very fast energetic CMEs. And then lastly, solar radio bursts. And the solar radio bursts are produced by non-thermal electrons. So these electrons are also accelerated by the shocks. And there are other mechanisms by which energetic particles can be produced. And I have explained that in the right-hand side picture. You see, I mentioned flux ropes. So the CME cross-section looks like a helical magnetic structure. And then this is the reconnection region where I have put a small current sheet here. And this is the flare structure at the bottom. We also call it post-eruption arcade because once the eruption happens, then you see a bright loop arcade sitting at close to the sun. So this is the flare, and then the other one is the mass ejection in the upper portion. Now, when the CME is fast enough, it drives a shock, as I indicated with thick line. And so this is kind of a generic picture of a solar eruption. And in the middle, you have a little elliptical structure here. This is a prominence. You might have heard about solar prominences. These are cool material that go along with the CME as the center of the CME. So what you see in this picture, there are two locations where particles are accelerated. One is at the shock, and one is in the flare reconnection region here. So the arrow marks point to plasma flows inside, and there is reconnection, and then plasma flows out as the CME. And these energetic particles produce various electromagnetic signatures like radio bursts in microwaves. And the accelerated electrons go down and bombard the chromosphere, producing X-rays and gamma rays. And the energetic particles accelerated the shock front, they typically go out, and if you are somewhere in the path of these particles, then we record an energetic particle event. The same shock accelerates electrons. If the electrons are 10 keV, for example, they form an unstable system with the background plasma. So you have a background plasma, which is a 1,000,000-degree coronal plasma. And then you have these high energy particles, 10 keV particles superposed on that. Then you get a configuration known as bump on tail. And this configuration is unstable. And the bump represented by the energetic particle population has to be leveled off. And that happens when those energetic electrons give out Langmuir waves. And these Langmuir waves interact with the low frequency waves, and they emit and they convert themselves into electromagnetic emission, which we observe as radio bursts. One particular burst is called type 2 radio burst, basically coming out of the shock accelerated electrons, which is relevant to the talk today. So remember, this type 2 burst is nothing but electromagnetic emission produced by electrons accelerated the shock front. Okay, so this basically explains the terminology I'm talking about. Now, the CMEs have very interesting space weather consequences. For example, the energetic particles constitute particle radiation hazard. When you are beyond the magnetosphere, you are directly exposed to particle events from the sun, and they can cause single event upset in the electronics. Instruments can be destroyed, or the entire missions can be disabled. You have dielectric discharge taking place in the surface as well as deep interior. And the particle radiation can also cause dosage to astronauts, and even for airplane passengers, if they are flying in a polar route airplanes. Because you recall I mentioned about energetic particles from the CME hitting the SOHO detector and producing all this flickering. And those particles are actually secondaries produced by the interaction between incoming particles and the detector or the metal of the spacecraft. When the mass ejections come and hit Earth's magnetosphere, then the solar magnetic field and Earth's magnetic field can temporarily reconnect. And then you have a situation where the solar field is connected to Earth's field. And that leads to what is known as geomagnetic storms. Basically, you have a reconnection in the day side, and that pushes the magnetic fields to the back of the night side of Earth. There is another reconnection, and from there you have particles injected into Earth's magnetic field, causing what is known as a ring current. And that is, the ring current can actually temporarily reduce Earth's horizontal magnetic field, which is typically referred to as a geomagnetic storm. Now, these particles can also enter into the magnetosphere and get trapped in the Van Allen belts, especially the inner belt for protons. And during geomagnetic storms, a lot of waves are created in the magnetosphere. So these waves can accelerate electrons through wave-particle interaction, and you get relativistic electrons inside the magnetosphere. And as you know, we have many, many satellites inside the magnetosphere. All these satellites are vulnerable because of these relativistic electrons accelerated inside the magnetosphere. So you can see CMEs have various important consequences for human technology on Earth and in space, because sometimes you can have what is known as geomagnetically induced current on the surface of Earth, and that current can damage transformers. It happened several times. One in 1989 Quebec in Canada was completely blacked out for almost half a day. And then in 2003 in Sweden, October 29, I think, Sweden, a transformer was completely burnt out because of the surge current produced by a geomagnetic storm. So, of course, we are interested in a new phenomenon, which is known as gamma rays. And these gamma rays are related to the CMEs via solar energetic particle events. So one thing you want to note is that the CMEs causing solar energetic particle events are very fast, more than like 1500 kilometers per second. They are very wide. And also they originate on the western side of the sun. Because sun's magnetic field in the interplanetary medium has a Parker spiral shape because of solar rotation. And therefore, Earth is connected to the western hemisphere of the sun magnetically. Therefore, if you have an event happening on the western hemisphere, you see a big energetic particle event at Earth. On the other hand, for the CMEs causing geomagnetic storms, they are also equally energetic. About 1000 kilometers per second is the average speed. And they are also very wide. And the source locations of those CMEs is very close to the disk center of the sun, where you can see the difference between the top and bottom. This is because CMEs originating from the center of the sun, they can directly come and hit Earth. Okay, so we are interested in energetic particle events because they are related to solar gamma rays, as I'm going to illustrate. Now, solar gamma rays, as you know, they were first predicted by Phil Morrison in 1958 and first observed by the OSO 7 gamma ray monitor. So there are three types of gamma ray emissions known associated with solar eruptions. One is the gamma ray line emissions, and these are from excited nuclei or newly formed nuclear products due to bombardment of particles with the solar atmosphere. And these typically have an energy range of about half an MeV to 8 MeV. So it's at the lower end of the spectrum I've shown here. And then Bremsstrahlung is caused by energetic electrons bombarding or interacting with the particles. And this source of these electrons and positrons actually are due to charged pion decay. So first you have to produce charged pions, and then the charged pions decay and produce electrons and positrons. These electrons and positrons then produce Bremsstrahlung. So the energy of these gamma rays is up to the energy of the source electrons and positrons. And finally, the pion decay gamma ray emission, and this is caused by neutral pions, again due to the bombardment of protons from the corona hitting the solar atmosphere. And the pi zero decay has a characteristic peak around 68 MeV. And you can see the bump in the rightmost bump in the plot. And you can see these various ranges, and there are detailed lines. Many lines have been identified, include, for example, the neutron capture line, the annihilation line, and so on. Okay, so today's topic is about sustained gamma ray emission. So what is it? So when you have a solar eruption, you have solar flare and coronal mass ejection. The solar flare is a prompt emission that happens immediately. Then you have particles accelerated. Those particles go down to the sun and produce X-rays and gamma rays. This is called impulsive phase emission as well. But then during an event in 1982, June 3, Forrest et al. Found that there are two types of spectra. First, you have this Bremsstrahlung, which is the energetic electrons hitting the chromosphere. And then later in the event, you have this bump corresponding to the pi0 spectrum I mentioned before. So you have this compound spectrum, which has a bump here, which looks like a giraffe neck. And this spectrum is characteristic of pi0 decay. And these pi0s are produced by more than 300 MeV protons. That's the threshold. So if you have protons with energies more than 300 MeV, they definitely produce pi0, which decays into gamma rays. And the important discovery of Forrest et al. Is that these particles are different from the ones causing the flare emission. And they suggested that the spectrum or the process may be similar to the ones which produce solar energetic particle events. So that's a very initial suggestion on the origin of these 300 MeV protons. Of course, they do exist in the flare reconnect site as well. So if you go back here, so in this location, the flare reconnection site, you have both electrons and protons accelerated. And these protons can flow down and produce gamma rays. And in the event I just mentioned, they did find a gamma ray emission coming from pi0 decay during the flare reconnection. But then after the flare ended, there was continued gamma ray emission after the flare ended. So that is the one which people call as long duration gamma ray flare or late phase gamma ray emission and so on. Late phase because it is after the flare peak when the event is decaying and lasts much beyond the end of the flare. So in this case, they observed this a couple of minutes for the impulsive phase of the flare, and then the flare peaks and then it decays. But about 10 minutes after the flare, also they observed this emission. And that's why it is called long duration emission. Now we call this sustained gamma ray emission because the flare has ended, so you don't want to call them as flares when the flare is ended. So people came up with this new name, sustained gamma ray emission, because it is sustained by some other process, not the flare. Okay, now I said it 10 minutes was the duration of this extended gamma ray emission. But then Akimov et al., they identified an event from the gamma mission where they found, so the red arrows indicate the duration of the flare. And of course, the observation started a little bit late, but then they observed this extended emission, which lasted for more than 2.5 hours. And the flare ended right here. So that's why people don't want to call this as flare emission, rather than it is some kind of sustained gamma emission. So who sustains this emission is a question. By the way, this was the first time gamma rays were detected at energies more than 1 GeV. And then the spectrum is very consistent with the late phase emission that Forrest et al. Identified. In another event, actually from the same active region, the duration of the gamma rays was even much longer. So here is the time versus count rate for these gamma rays, and this is the flare start time. And you can see that the emission extended for more than 8 hours. Because this is, so you need to have some source on the sun that keeps accelerating particles for many hours. But we know flare accelerate particles only for a couple of minutes. And we are talking about many hours. So what is the other possibility? And that is the shock. As I mentioned, the shock driven by CMEs can be observed when the CME arrives at Earth. That means for a couple of days, the shock is accelerating particles. So if you are looking at looking for a source of energetic particles, then the shock is a very good candidate. And it was already mentioned by Ramati et al. In 1987, also Murphy et al. In 1987. And they suggested that the particles responsible for this kind of extended emission may be coming from the shock, and these particles go to the sun in addition to going out, which we detect as SEP events. So from the shock, you can have particles going sunward, they produce gamma rays, and the particles go earthward or outside, away from the sun, we can detect them as SEP events. Okay, now comes Fermi. So you might have all seen this beautiful picture from all-sky image taken by Fermi. And you see all kinds of sources. You have supermassive black holes, merging neutron stars. And so you can see SNRs and supernova remnants and sources like this. And pulsar here is a Vela pulsar here. So compared to this, of course, sun doesn't do that much, but occasionally the sun can be the brightest star in the sky in gamma rays. So that was really a big surprise. And what you're seeing here, where I marked sun, that is the emission, extended emission I was talking about. When there is an eruption, of course. Other times, also sun produces gamma rays, but at a very low level. And that is from a different source of particles. You can imagine, because if you have a galactic cosmic rays coming from outside our heliosphere, they enter into this heliosphere. Some of them go and directly hit the sun. And then by the same mechanism, they produce gamma rays. And in fact, this was one of the earliest plots made by the Fermi team member Giglietto. And you see three components. The green one is the disk emission caused by these cosmic ray protons I just mentioned. You can see that. So this is the elongation angle. So the sun itself is half a degree here. And then you have this pink line, which is the inverse Compton emission. You have electrons and positrons from the cosmic rays coming close to the sun, interacting with solar photons and produce inverse Compton emission. And that is actually very extended. You can see that it goes up to 18 degrees or so from the center of the sun. So it's a long distance from there. And this is also called halo emission, but they are a very low intensity. So what we are interested here is this right at the top. This emission is caused by solar protons. Here is another plot, a spectrum of solar disk emission in gamma rays. So you can see that the purple ones are the full data set from 100 MeV up to 100 GeV. If you look at the spectrum before less than 1 GeV, you see that the emission is very high. And these are all caused by solar events, which are superposed on the disk emission, which is happening most of the time. So if you remove the solar flares happening during this interval, then you just see the disk emission, mainly from the cosmic rays. So basically, cosmic ray protons and the protons generated by CME shocks, they do the same thing at low energies. Of course, cosmic ray particles have much higher energies as well. But at higher energies, you don't see these solar events because they are confined to typically below about few GeV. Okay. Now let's look at a typical event. And here is an event from Agello et al. In 2021. They published a catalog of more than 40 gamma ray events. And I want you to look at the bottom panel. The red dots are the measurements from the flux measurements from Fermi lat. And you see initially there's a spike, which lasts for about a couple of minutes. And then after that spike ended, then you have slow, gradually going up, something going up and lasting for tens of minutes. So this is the sustained gamma ray emission, and this is the impulsive emission. And it is tempting to associate this impulsive emission with the solar flare, which is again the X-ray solar flare plot at the top. You can see it happens before the peak of the X-ray flare. Whereas this sustained gamma ray emission has no relation to the flare at all. And Fermi also has a low energy telescope known as GBM, gamma ray burst monitor, and that observed the impulsive phase, that is the flare component, as this is up to 40 MeV, this is up to 1 MeV. And you can see that the emission just is confined only to that portion. Because Fermi has this high energy detector, it's able to detect the sustained gamma ray emission. So this is the enigmatic process, and people have been trying to understand this. So one idea, as I already mentioned, is that the shock produces these particles go back to the sun and produce gamma rays. And the other idea is particles accelerated during this flare somehow get trapped in flare loops, and they live for hours, slowly diffusing and producing gamma rays. Obviously, there are some issues with the number of particles accelerated and how they can live in coronal loops for that long it requires some tailored specific level of turbulence present in those loops. All right, so basically I will be contrasting between these two possibilities, one produced by flare reconnection and trapped in the flare loops, and the other accelerated by the shock. And we have definite information about the shock, because the shock sometimes arrives at Earth. And even at Earth, they accelerate particles, but to low energy. So we know that shock is accelerating particles. And the flare also accelerates particles, we know, but we do not know about the required turbulence level in those loops. In fact, some people require turbulence to re-accelerate those particles, something similar to what I mentioned in the magnetospheric situation. But for example, the Kahnbach et al., who observed the 8-hour gamma ray event from Egret, he thinks that the loops should not have any turbulence if you want to keep the particles for a long time. So that itself is a big problem. All right, so let's look at this event, what happens on the sun in terms of eruption. So you have a solar eruption flare happening in on the disk, and then you have this mass ejection coming out. And this mass ejection accelerate particles, as we know, at Earth, GOES measured these particles. You have 10 MeV, 50 MeV, and 100 MeV particles. So 300 MeV is pretty close to this one. That means you do have extended period of particle production by the CME shock. And also the CME was associated with the type 2 radio burst. I mentioned that type 2 radio burst is caused by the shock, and in radiodynamic spectrum, they look like this slanted feature, and maybe there's a weak event continuing as well. But this is really strong type 2 radio burst emission, indicating shock acceleration of electrons. Now, here is another event from Fermi-LET again. The red shows the gamma ray emission, and the blue shows the X-rays. And again, you see the flare ended, and the peak of the gamma ray emission is well after the, so you can see that it is 0 to 12 hours, so the hours after the end of the flare. And we looked at about 24 big events, and the duration of the gamma ray emission is typically about 10 hours. And as I mentioned, the flare is typically minutes compared to 10 hours. So here is an event which illustrates all these things I mentioned. So you have a CME coming out from the sun, observed by stereo. And it's also observed even up to 90 solar radii through extended field of view of stereo. And this is the type 2 radio burst. And you can see, and then this is something known as type 3 radio burst. Don't worry about it. That is the electrons accelerated during flare. And then this white line with the dots is the gamma ray emission. And this white line without dots is the SEP, solar energetic particle intensity. So what you see is this gamma ray emission ends here where the type 2 ends. Right? So the type 2 burst is basically caused by 10 keV electrons, and the gamma rays are produced by more than 300 MeV protons, but they roughly end at the same time. So which means somehow the acceleration of electrons and protons seem to be happening simultaneously and ending simultaneously. Okay. Now, at this time, when you have the type 2 ending, the CME is already up to 65 solar radii from the sun, about a third of the sun-Earth distance. Okay, now you can see that the close connection between the electron acceleration by the shock, indicated by the type 2, and the proton acceleration, indicated by the gamma ray emission. So you have emission coming down from about 10 megahertz to down to 200 kilohertz, right? So you have kilohertz emission and the zetahertz emission are related. Now this is not isolated event, maybe coincidence, but actually no. If you look at all the big events, for example, if you consider gamma ray events with duration more than 3 hours and plot the duration of the gamma rays as a function of type 2 ending frequency. The type 2 ending frequency corresponds to some kind of distance from the sun, because near the sun the frequency is high. As you go away from the sun, the frequency decreases, because the type 2 burst is caused by plasma waves, and the frequency of plasma waves depends upon the plasma density. And as you go away from the sun, the plasma density decreases, therefore the emission frequency decreases. So this negative correlation basically means that gamma ray emission lasting much longer, they have ending frequency much lower. That means farther away from the sun. You can also plot the gamma ray duration against the duration of the type 2 burst, which I showed in the movie. And you can see that they are well correlated. That means somehow the duration of the gamma rays and the duration of the type 2 bursts are related. And you can understand by the shock process where the electron acceleration and proton acceleration end around the same time. So this is an important new addition to the original idea that the particles may be accelerated with the shock and they go back to the sun to produce gamma rays. Now we are looking at a large distance from the sun, because the type 2 bursts are in the interplanetary medium, and as I mentioned, up to a third of the sun Earth distance. So this means that you can have particles propagating back to the sun from the heliosphere. And here's the scenario that we proposed. So here's the sun, and you have these flare loops. They produce impulsive gamma ray emission. But then the CME, it drives a shock. This shock accelerates both electrons and protons. Protons go outward, and if Earth is in the path, you can detect them as a SEP event. And then they go down and produce gamma ray emission. But they don't go to the flare loops, but in the surrounding region. One thing you can infer from this scenario is that the gamma ray source has to be much more extended than the flare itself. And here is an event which produces gamma rays. So what you're looking on the left-hand side is a magnetogram, a small patch of the sun's disk. And the white is positive magnetic polarity and black is negative magnetic polarity. And these green lines indicate the flare ribbons. So the flare structure is confined to the high magnetic field region of the active region, sunspot region. And then you have a location of the CME flux rope far away from the flare site. And this is the extended emission I was talking about. What is interesting is that the magnetic fields in the region where you expect the gamma rays coming from is very low compared to the active region field. Keep this in mind because this is important in understanding the difference between the two. On the right-hand side is the same thing. This is an EUV image showing the flare structure, this bright feature here. And these are the legs of the CME flux rope. In fact, a long time ago, there was a gamma ray line emission from a solar eruption that took place about 10 degrees behind the limb. And Kleiber et al. Interpreted this event as an extended shock from behind the sun, but then some portion of this shock can come to the front of the sun and deposit particles close to the limb, and they produce gamma rays. As you know, the gamma rays happen very deep in the atmosphere, close to the photosphere, or sometimes even below. And those gamma rays, if it happens on the backside, they cannot penetrate the sun and come to the front. So somehow these particles accelerated by the shock, they have to precipitate on the front side to produce gamma ray line emission. But of course, it was only 10 degrees behind the limb. It was a little bit not clear, because sometimes the flare structure can extend to the front. But in 2014, there was another event from an eruption that took place about 40 degrees behind the limb, way behind the limb. And in that case, absolutely, there is no way the flare can send particles to the front side. So it has to be a shock that is extending from, that means the shock extent has to be more than 80 degrees, 40 degrees on one side, to be showing up on the front side and depositing particles on the sun. So this is that event. So this is Earth view, and this is Earth view of the sun. And the green is the CME flux rope structure, and the pink is the shock surrounding the CME flux rope. And the blue dot represents the location of gamma rays in this event. Now, it is clearly the event is happening behind the east limb, about 40 degrees behind the east limb. And fortunately, we had a stereo observing the same CME from behind the east limb. So it was able to look at the source details. Although it was hidden from Earth view, stereo view had this. This is stereo view. And you can see a flare structure here. And then you have this dimming region, which are the legs of the flux rope I mentioned. So this green flux rope has one leg. This leg, one leg is here. The other leg, deeper leg, is over there. Okay. So now if you have a CME coming like that, such a flux rope, D1 and D2 corresponds to these two locations. If you have a big flux rope coming out, then the surrounding shock obviously can extend to the front side. And you can see that the extension of the shock on the front side. So I think this is a very clear example where you have to have an extended source, which is the shock, so that it produces an extended gamma ray emission. So if gamma ray emission is happening here, it should be happening at different locations in the backside. All those photons did not reach us. Only the ones which are the edge of the region came to us. So this tells two things. One is the accelerator is extended, and then the particles are precipitating over an extended region. Now the flare mechanism depends on these loops. Okay, so this is basically an arcade. So you have loops here. The bright regions are loops, and you have to trap these particles, and there is no way these particles can come to the front side to produce the gamma rays. So this is a very clear evidence obtained by Fermi. Also remember that the flares are very compact, this arcade, whereas the shock is much more extended. And here is the same thing is illustrated here. The green, this is the flare arcade, and this is the CME flux rope. All right, there's one event in which they were able to identify the motion of the gamma ray source. Initially, so here is the flare structure of another event. And the gamma ray emission was initially found, and later on it was found here, which is spatially separated from the initial flare location. Very similar to the September event I just mentioned, because you can have gamma ray emission coming from an extended region. Now it's 2 o'clock. How far can I go? Can I stop or should go?
We don't have any bell, so going to the end.
Okay, great. So I'll be done in maybe 6-7 minutes. Okay, now let's go back to the CME properties. There is one kind of SEP events known as ground level enhancement. So energetic particles from the sun can come all the way to the ground on Earth. Typically, of course, in high latitudes, it's easy for the accelerated particles arrive at ground-based neutron monitors. Okay, so the primary particles from the sun produce neutrons when they interact with the atmosphere, and then neutrons can be detected, and then we can understand about the primary protons causing those neutrons. These are called ground level enhancement because you suddenly see increase in particles. And this was actually identified by Scott Forbush in 1942. And in 1946, he published a paper connecting the particles observed on ground to solar eruptions. Now, these are the most energetic SEP events, right? Because GLE events have particles, primary particles up to maybe 10 GeV. So GeV particles are arriving at Earth from solar eruptions. And these particles are accelerated by the CME-driven shocks, as I mentioned. Interestingly, all known GLE events are also SGRE events. Right? It's no-brainer because GLE events means you have particles accelerated to GeV energies. And if particles are accelerated to GeV energies, they have to go past the 300 MeV particles first. So you should have copious production of 300 MeV particles, and therefore they can produce gamma ray emission. So what is interesting is the CMEs associated with the SGRE emission have this properties very similar to those of CMEs causing GLE. Again, it's obvious because both need high energy particles. SGRE need more than 300 MeV, and GLE needs about GeV to reach ground. Okay, so for example, the speed of the CMEs associated with the SGRE is about 2,000 kilometers per second. Here is a histogram. The average is about 2,000, and it's more than 1,000. The lowest is about 1,000 kilometers per second. And all SGRE CMEs are halo CMEs. So I did not introduce this topic. Halo CMEs basically means that if you look at the CME, it appears to surround the sun. But in reality, it is not surrounding the sun. It is like a cone with its base towards us and the apex close to the sun. And therefore, in skyplane projection, the CME appears to surround the occulting disk of the chronograph. And these are called halo CMEs. And this is a kind of selection effect. If you have a halo CME, that means you are looking at a fast and wide CME or energetic CME. And that explains why all SGRE are associated with halo CMEs. That means they are associated with very wide CMEs and fast CMEs, as I already mentioned, therefore very energetic CMEs. And also, the gamma ray associated CMEs have type 2 bursts extending to kilometric wavelengths. I showed this negative correlation before. And this property is similar to GLEs as well. And most of the SGRE are associated with M or X class flares. There's only one C class flare. Mostly these are major flares. As you know, flares are classified A, B, C, M, and X. X are the most intense solar flares, M are medium, and C are kind of marginal. And then you have B and A, which are very low energy flares. What is interesting is that the GLEs are associated with M and X class flares. Now, all these properties are shared by GLE associated CMEs. Okay, so this implies that GeV particles are accelerated by these CMEs. And then sometimes you don't see these GeV particles at Earth because Earth may not be connected to the right part of the CME. So sometimes you see a soft spectrum event, but it is not due to the acceleration process, but it is due to the connectivity process, because energetic particles travel along field lines, and these field lines should connect the source of the particles to Earth. Then you see the particles. Sometimes, even though particles are accelerated, if you're not connected properly, you may not see the high energy particles at Earth, but still they produce gamma rays. Now, there's one interesting thing that you can infer from so far what I said. I said the gamma ray duration is about 10 hours. You remember the histogram? This is the average duration. And the average speed is about 2000 kilometers per second. With this speed, how far will the CME be after 10 hours? And that is something like 100 solar radii, midway between Sun and Earth. So these shocks seem to be accelerating particles up to about 100 solar radii from the Sun, midway between Sun and Earth. And from midway between Sun and Earth, particles go upward and downward particles produce gamma rays. Now you see this cumulative distribution of CME speeds. And this is the number with exceeding a particular value cumulative distribution. And you can see all the energetic events, they happen at higher speed than the average speed. This is the 400 kilometers per second we saw in a histogram, right? So all the special ones, the ones produce radio burst, interplanetary coronal mass ejections, geomagnetic storms, halo CMEs, SEP events, and the GLEs, the last one I talked about. And SGRE is so it's very similar to this one. Okay, so you can see that these are basically extreme solar particle events are the ones which are responsible for the gamma ray emission. And you can see further connection. You see the CME speed and the gamma ray fluence. They are very well correlated. So that means the CME has something to do with the gamma rays. And then, so this is basically establishes the close connection between the SGRE and very energetic CMEs. Now, if this same shock produces SEP events that we observe by particle detectors, let's say on GOES, and and then let me rephrase. So there is a close connection between the shock and the gamma ray emission, as indicated by the CME speed and gamma ray fluence. Now, the connection is that these CMEs accelerate particles, and those particles go back to the sun and produce gamma rays. Therefore, you do expect some kind of relation between the number of particles observed as an SEP event in an SEP event like GOES, and the number of particles that you can infer from the gamma ray intensity, right? Because to get certain number of gamma ray photons, you need certain number of particles. So you expect a correlation between the number of particles inferred from gamma ray event and the number of particles observed directly as a SEP event. So this is the correlation. Dinolfo et al. In 2019 produced this plot where they plotted the number of protons inferred from gamma ray emission and the number of protons observed in the associated SEP event observed by Pamela spacecraft in this case. So what do you see here? You see there is no correlation. The correlation coefficient is 0.43, which is smaller than the Pearson critical correlation coefficient. Therefore, the correlation is not statistically significant. So this is a big challenge to the shock idea. Right? If you have a shock idea, then if the shock produces both particles for gamma rays and particles in a SEP event, then they should be correlated. It's not correlated. Therefore, the shock idea is nonsense. Now, there is a problem in this plot. If you look at the source locations where these are happening, if you look at these two events, which are away from the central location, they are from much higher latitudes. This is happening at north 28, and this is north 31. Now, if this is the direction in which the CME is heading out, and you know 0 is the ecliptic, so this is 31 degrees away from the ecliptic, and this is 28 degrees away from the ecliptic. If the particles are accelerated, let's say within about 10 degrees from the nose of the shock, then in that region is not connected to Earth, so you won't see high energy particles. Therefore, you will underestimate the high energy particles. But if you look at the ones on the right side, so this is the blue ones are the one I talked about, high latitudes. But if you look at the right side, the ones, look at the longitudes of these events. They are all close to the limb. So East 127 is behind the limb. This is the one we talked about, the September event, 2014 event. And East 82, West 71, West 76, West 89. So there is something systematic about this. The high latitudes ones on the left side, the high longitude ones are on the right side. Okay. Now, so if the source of this high energy particles is confined to a small region on the shock, then you're underestimating. So if you correct for that effect, the number of protons inferred from the SEP event is underestimated. So these particles will move, the points will move to the right. Okay, because you're underestimating the proton number. But if you look at the gamma ray events, these are close to the limb. And recall that I said the gamma ray source is extended. If the gamma ray source is extended and we are looking at events close to the limb, then part of the gamma ray emission is behind the limb and we are not receiving them. So we are underestimating the gamma ray flux, and therefore we are underestimating the number of protons inferred from the gamma rays. So in this case, they also have to go move up because we are underestimating them, the proton number here. So they go up. So if you move them to the right and move them to the top, then you can see that they are going to align very well. And so this is the detail I mentioned about the extended source. Let me skip. So, okay, so here is the idea. EV particles are accelerated at the nose of the shock. And so the 300 MeV protons come from here, and the low energy protons come from all over the shock. Now, if you're not connected to this, you will see very less number of high energy particles. So you will see a soft spectrum event. And that's what I mentioned on the left side events. If you correct for those, you see how they are moving. The left side events move to the right side events move to the top. And there are some red events which are not moving because they are in the right location. So you do not need any corrections. They are not at high latitudes. They are not at high longitudes. Okay. So if you make this correction, then the correlation jumps from 0.46 to 0.71. And this is a very significant correlation. You remember the RC is 0.46 and the R was 0.43 before. And then in fact, there is one event which is an outlier, and Jerry Scher found that this event probably is not the sustained gamma ray emission, rather it is the tail of the impulsive phase emission. Well, even if you remove that outlier, then the correlation goes to 0.77. So whether you include this or not, still the correlation is very high. Therefore, the argument by Dinolfo et al. Does not hold, because there is a good correlation between the two numbers. I think this is the most recent work that we did to basically strongly support the shock idea. Now, there was one event which has got a big SEP event, a big CME, a big radio burst, but there was no gamma ray emission. So this could be a counterexample that a big particle event may not be producing gamma rays. But then when you look at the Fermi layer data, which is shown in this orange curve, you see during the critical period from the beginning of the flare to the peak, there is no observation. And beyond the expected region, you have 2 data points well above the background. Of course, if you do not have this information, you won't consider this as an event because these are not 4 sigma events. But if there was a data point here, then this can be probably tail of the SGRE emission. So you cannot conclusively say there was no gamma ray emission because of the Fermi data gap. So it looks to me that that all energetic particle events with hard spectrum or more than 300 MeV particles, they do produce gamma ray emission. There are a couple of outstanding issues. I will skip that, but I want to point out one other criticism of our work, and that is mirroring. When particles are flowing back to the sun, they are going towards higher magnetic field because the magnetic field at the sun is higher and the interplanetary medium is lower. Therefore, the particles will hit a location where they mirror back into the interplanetary medium. So they may not be able to interact with the atmospheric protons to produce pi 0 and then gamma rays. So what's going on? This is based on a Hutchison et al. Did a simulation and showed that these particles may not be able to reach the required level to produce pi 0. But the problem with this simulation is that they don't realize that the gamma ray emission is not coming from the high magnetic field active region, but in the quiet region because of the extended nature of the gamma rays. And therefore, the mirror problem is actually non-existent. In fact, it may be useful because the particles are going in the quiet sun region, therefore they reflect very deep below the photosphere. And then on the way back up, they produce gamma rays, and that's good. And this was actually shown theoretically by Sekel et al. In 1991, where they considered the interaction of cosmic ray protons with the solar disk. And we have very similar situation in the case of SGRE, and therefore this mirroring problem is not significant. So there is second objection that has been also countered from the work of Sekel et al. 1991 for galactic cosmic rays. But over the same energy range, it should not be any different because protons of certain energy is what matters. And this is the one I showed before. So people are considering mirroring here, but actually mirroring should take place here where the magnetic field is very, very low compared to the active region field. Maybe it's a couple of Gauss compared to 1,000 Gauss. So therefore, the mirroring issue is probably not significant. All right, and this is the quiet sun magnetic field, and the kilogauss field exists below the photosphere right here. And Sekel showed that particles can bounce off here, whereas Hutchinson et al. Talking about the particles reflecting way up here. So the main problem is Hutchinson et al. Did not realize that the precipitation of particles is taking place in the quiet region, not in the active region. Okay, I think you have a new event started in cycle 25. About half a dozen have already been observed, and the properties as well as the details look very similar. So I will not talk about this and go to the summary. So I hope I was able to give you an idea that Fermi-Lat observations have revived the source particles controversy of sustained gamma ray emission. And I hope you appreciate the close connection among SGRE, coronal mass ejection, solar energetic particle event, and type 2 radio burst, because they are all related to the CME driven shock. And also I showed that the SGRE associated CMEs are very similar to GLE associated CMEs. That means high energy SEPs are guaranteed. The CME speed is closely correlated with SGRE fluence, which further supports the connection. And the soft spectrum SEP events, I mentioned this in the beginning. Sometimes because of connectivity, you will see a soft spectrum SEP event. But actually, if you go back and look at the nose of the shock, it is not a soft spectrum event, it is a hard spectrum event. And that is purely due to magnetic connectivity. And then the last point I showed was the extended source is extended source of gamma rays results in the number of SEPs and the number of particles derived from gamma rays have a correlation. And the extended emission is similar to the quiet sun scenario proposed by Tsekal et al. In 1991 for the interaction of galactic cosmic rays with the solar magnetic field. So there are a couple of events I did not have enough time to talk about. There are two events where the CMEs are not observed, but still you observe GRE. So people might think that these are counterexamples for flare emission, but actually there are some CME signatures indicating that maybe you are not really observing the CME, but CME exists in the form of, for example, EUV shock-like structure very close to the sun. So that's all. Thank you very much. I'm sorry I'm a little bit delayed.
Well, thank you very much, Nat. Are there any questions?
Yeah, actually, I do have a question that I'm quite amazed at the analysis that Nat has gone through to support his view on this. This is sort of a completely new idea that I was not familiar with when I was actually active in the field too. But I'm amazed at the work he's been doing. I do have a question that occurred to me during the talk. It appears that the magnetic field that threads the shock has to connect back to the sun in order for the particles that are being accelerated by the shock to get back to the sun. And so I'm just wondering, yeah, that for example, that scenario there is where I began to appreciate this, that those field lines are not necessarily associated with the original CME. Is that?
No, these field lines are not associated with the CME,
right?
But they are in the medium surrounding the CME in the sheath region between the CME and shock, and the particles travel along those field lines. So this is the important point about the mirroring. If you look at this one here, so that's the flux rope or the CME structure,
Yes.
and the surrounding field lines along which the protons propagate and precipitate.
Okay.
And the shock is actually supplying the particles to these field lines. So the CME effect is to drive shocks, and these shocks supply particles to these field lines, and they go and precipitate at far away from the flare site.
Okay. Well, the question that occurred to me is, where do the particles that are being energized come from when the shock is accelerating? Are the particles being picked up from the solar wind? Are the particles
Yes.
streaming up?
This is from the solar wind. They pick up from this region. They pick up, but there may be a situation where there are multiple CMEs. Maybe there is a preceding CME that happened. Actually in one of the events I showed. Yeah, here. So this is the CME, and this is the particle event. And there, from the same active region, there was another CME which produced low levels of particles. So when the second CME happens in the medium, already you have a population of low energy SEPs, and this CME can accelerate these particles. So in those cases, the CME need not be very energetic because they have to be, they have already accelerated particles ahead of them. And in fact, this CME is only about 1,000 kilometers per second, 1400 maximum. So I think that is a very good question. But if you do not have these particle events, then the CME has to be very energetic.
So that would explain why you need these very energetic halo events to create the SGREs in the first place, I guess.
Yes, you're right.
And, the other question that occurs to me is that since you have connection from the shock back to the sun, the photosphere, and the chromosphere, don't particles from the sun travel on the same few lines up to the shock? In other words, you've got particles not only going down to the sun, but coming up from the sun back to the shock.
But there is no source of those particles in those regions. Because so the moment they turn back, they are already, they interacted with the ambient particles and they lost their energy. And that is the energy going into pi zero, which decays into these gamma rays. So there is no source of particles coming back along those field lines. Of course, there may be some, isolated particles from thermal distribution can go, but there's no significant number of energetic particles present there because they all deposit their energy, lose their energy at the high density region.
But are there not field lines from the shock that connect back to the sun far away from where the original flare took place? That would then provide sort of a low energy population of particles that might be a seed for acceleration in the shock?
So the seed particles have to be here ahead of the shock, and it should be here. There should be particles, and then this shock accelerates more efficiently. But there's no seed particles. Then this will basically take the coronal particles, the ambient particles, and accelerate them. So that in that case, when there is no seed particles, the shock has to be very strong. The CME has to be very fast. But if there are seed particles, even a slower CME can do it.
Okay. Actually, that raises one of the other questions I had, was that it was very interesting to see that figure where the type 2 burst and the SGREs end at basically the same time, about 100 solar radii. Yes. What happens there in that suddenly it's sort of a cutoff in the numbers of particles available to the shock, or
I think the shock loses steam because the CME decelerates. You remember I showed an acceleration plot where because of the high speed of the CME, the drag force acts on the CME because the drag depends upon the surface area of the CME and the ambient density and the speed difference square. Therefore, when the CME is very fast, it's subject to very high drag force. So usually the CME slows down, but it may still be accelerating particles, but much lower energies, like 50 MeV, 10 MeV particles. If they accelerate, they are not going to produce gamma rays.
Okay.
Because sometimes when the shock arrives at Earth, it still has some particles, low energy particles accelerated, but then they are in the range below 300 MeV, therefore they cannot produce gamma rays.
Okay. So I don't know if you have enough statistics, but has that sort of cutoff point pretty much located at about 100 solar radii, or is it?
See,
No.
even sometimes even a little bit further, like 175 is the highest we have seen in an event in January 2012. Because in some cases, the duration of gamma rays is like 2 times the distance I'm talking about. Here is 65, and then sometimes the gamma ray duration is like 23 hours. So in that case, this is for 10 hours is like 100 solar radii, and if it's double that, it's even like 175.
Mm-hmm.
So yes, it is very, but of course, people are taken aback when this idea was proposed, but there is no reason, because magnetic field lines carry particles, and if you inject them in different directions, they will take whichever direction you inject them. So the shock injects particles on both front and back. So therefore, there is no reason they should not go back to the sun.
Mm-hmm. Very good. Yeah, I am still.
Your former colleague Jerry Scher did a lot of work, and you know,
Yeah.
he was very happy to see this finally is getting resolved.
Yeah.
Okay, well,
Is LASCO still functioning?
Say it again, Paul.
I was wondering if LASCO is still functioning.
Yeah, it is. It is. In fact, it is even better because the cadence is higher now, because we don't have to download EUV images. So the cadence is increased, so it's doing well after 25 years.
Thanks, Nat. Yeah.
okay, there are no more questions? Okay, 2 things. Can you send to Paul a copy of your slides?
Sure, I can. Sure, I can do that. I think it may be a big. I will send a link, and you can download. So
Yeah, that would be
you
useful.
want me to email to who?
Yeah.
Okay,
Any one of you, Paul?
Yep. Yep.
Okay,
okay,
I will
and
do that.
okay,
Because the file is much bigger because of the movie, so I will send a link.
okay, I think that we recorded you. I hope we had your permission.
That's fine. I have permission. You can.
Okay.
Yeah.
Okay, well, we want to thank you for a very interesting talk. It's going to give us things to think about for some time.
Thank you. Thank you for the opportunity.
Thank you.
Okay.
Really enjoyed it.
Thank you. Enjoyed it
Alrighty.
very much.